So, okay. Look at the nucleus of a helium atom. It has two protons. They're positively charged. They want to repel each other. But in the helium atom, they don't repel each other. They stay together. Why is that? There's something in nature called the strong force. Okay? The strong force is a force that keeps the small particles of the atom in the nucleus glued together, stay together. It is stronger than the force of repulsion between the two protons. We call it the electromagnetic force of repulsion between the two protons, making them go away from each other, is strong. But the strong force that acts at very, very, very tiny and small distances between the neutrons and the protons, once they become so close to each other, the strong force is actually stronger than the electromagnetic force that repels the protons from each other. And so that's why the particles inside the atom of the helium molecule or other helium atom and other atoms stay together. They don't repel. All right? So what's after helium? After helium is lithium. Lithium is the third element. It has one extra proton. So one proton makes hydrogen, two protons makes helium, three protons makes lithium. Okay? So if it has three protons, then it must have three electrons. And there are indeed three electrons. You see, they're orbiting around the nucleus of the lithium atom. Okay? And it also has three neutrons. So it actually has 6 particles in the nucleus. So the atomic mass of lithium is 6 because it has 6 particles, 3 protons and 3 neutrons. Okay? So that's important to understand, and that's probably enough for now to understand what atoms are, because we'll understand more about that in future episodes, but for our purposes for right now, that's enough. So how do we organize all the elements that we find in nature? There are about 92 elements that occur in nature. The heaviest one is uranium, which is 92. It has 92 protons. The lightest one is hydrogen with 1 proton. The next one is helium with 2 protons, and so on. We'll study the periodic table in more detail, but this is how we organize all of the elements that we find in nature in a tabular form, and it serves a fantastic purpose that I will explain to you in other episodes. Well, here's something else about the atom that you should know that is very shocking. If you take the nucleus of the atom and blow it up to the size of a glass marble, you know, the marbles that you kids play with, the electron will be 120 meters away. That's unbelievable. That's how far the electron is from the nucleus, which means that whole distance from the nucleus to the electron is empty space. So actually the atom is 99.99999999996% empty space. How empty is that? Well, someone made a calculation. It's very interesting. They said, look, if you take all the 7 billion people on Earth and remove all the space between the electrons and the nucleus in every atom in their body and squeeze them all together, you can squeeze all human beings to the size of a sugar cube. That's how much empty space there is in the atom. That's amazing when you think about it. How does it work? We will study that in more detail later on in other episodes, but for now this is an interesting fact that will help us understand some of the things that we'll describe in the next episode. Okay, something else that we want to talk about is light. Light is a big part of our lives, and it all comes from the sun. And in fact, without light, we all die, because plants use light to make glucose and other chemicals in the plant that go in the fruits and the seeds of the plant that we rely on and the other animals rely on. So light is very, very important for life on planet Earth. But light has an amazing characteristics, actually. So when it reaches us from Earth, many things can happen. If it falls on a certain surface, it can be reflected back completely. Like when it falls on a mirror. When you stand in front of a mirror, the light goes from your body to the mirror, and then it reflects completely back from the mirror back to you. It doesn't go behind the mirror material. Okay, that's called reflection. Well, there's also absorption. Some materials can absorb light, so they don't reflect any of it. They just completely contain it within them, and they keep it. And other materials will allow light to go through. They don't reflect it, they don't absorb it, they allow it to go through, but they refract it. What does refraction mean? It means they make it change its angle. What's an example of that? When light hits water. Air is different medium than water. It's less dense. Water is more dense than air. 800 times more dense than air, actually. So when the light hits water, it changes its direction. It starts going in a different direction. That's called refraction. Okay? And so on. And so light has very many amazing characteristics, and we're going to study that in a bit more detail now. We see color. Where does color come from? That's what we're going to examine right now in detail. Look, this is a prism, right? You've seen that or heard of that, I'm sure. When light, which is white light we call it, comes in and reaches a prism, goes through the prism, prism material breaks it into the different colored lights that we see. And these are the colors that everybody is familiar with, right? We know these colors from when we are tiny children. They teach us those colors. What are they? There's the violet, there's the indigo, there's the cyan, right? And then there is the green, and the yellow, and the orange, and the red. These are the colors of light when they go through a prism. Does that happen in nature? Yeah, we see it in nature when you see a rainbow. That's what a rainbow is. Actually, there's a double rainbow here. You can see on the upper left there, there's a small faint rainbow. So how does the rainbow form? When light hits drops of water in the air, okay, when it's raining, and so water acts like a prism and breaks that white light into the 7 different colored lights that we have. And that's what the rainbow is. Now, so if you look at the different colors, why is something green and something orange and something white and something black? Why is that? Well, because let's take an orange color, for example. When light hits that orange object, all the wavelengths of light are absorbed by that object. The only light wavelength that is not absorbed by that object is the orange one. So that's reflected back. So that object is orange because it absorbs all the other wavelengths of light except orange. It does not like it. It throws it back at you. And that's why you see it orange. And the same for the other colors. You see this thing blue because when light hits it, it absorbs all the other wavelengths except blue. It doesn't absorb it. It reflects it back to you, and that's why you see it blue. So this is how we see color. So these I kept saying light is a wavelength, okay, which means it behaves like the waves of the ocean. It goes up and down like that in regular way. But the waves can go very fast like this, or they can go very slow like that. The faster they go, we call it the higher frequency. That means so many waves go within a certain amount of time in a certain distance. If you have in this distance so many waves going, that means the frequency is very high. There's so many waves in a short period of time within this distance. So if you have 1 or 2 waves going, that means their frequency is less. So when the wavelength is very long, the frequency is very low, and the energy is also low. Low energy, low frequency, low wavelength. When you have a short wavelength, okay, then the frequency is very high and the energy is very high. For the wavelength to go like this, it needs more energy. So violet wave is actually has very high frequency and it has higher energy than a red wave, which has slower, it has a bigger wavelength, okay, longer wavelength, but less energy and less frequency. So shorter wavelengths have high energy and high frequency. Longer wavelengths have a lower frequency and a low energy. Okay? So the light is nothing but an electromagnetic wave. That's what light is. It's an electromagnetic wave, which means it's electricity and magnetism joined together. The electricity is going this way and the magnetism is going perpendicular to it that way, and that's what light is. It's an electromagnetic wave. All right, so we measure the wavelength going from crest to crest. So if you look at one crest and then measure the distance from that one crest to the next crest, that's wavelength. Okay, and how high up the wave goes. Does it go this much or does it go this much? If it goes this much, it has higher amplitude than if it goes this much. So we call the distance of the wave from the base to the top of the crest amplitude. Okay? So the electromagnetic waves cover a long and very, very long spectrum. They can be very, very small or they can be very, very big. Well, let's take some examples of that. The light that we see, which are the 7 basic colors that I just explained to you, is actually what we call visible light. Okay? Visible means that our eyes can see it. Does that mean that there's light that is invisible that we cannot see? Yes, there's light that we cannot see. Any wavelength that is longer than the red wave is called infrared. We cannot see infrared. What's longer than infrared? Microwave. Like the microwave oven or the microwave towers that you see that send radio messages to your cell phone that you're using. And what is longer than microwave? Radio waves. Radio waves can be, the length of a radio wave can be as big as a house or as big as a mountain. So it can be very big. So these are radio waves and the very, very large wavelength. But the energy is less and the frequency is very, very low. Okay, let's go to visible light again and look at the other end of the visible light. What's the fastest and the most energetic wave in visible light? Violet. And we can see violet. So now what happens if you go to a frequency that is higher than violet and more energy than violet, but smaller, shorter wavelength? We call that ultraviolet. That's what ultraviolet is. Ultraviolet is a higher frequency than violet, more energy than violet, but shorter wavelength than the violet. And so the ultraviolet we cannot see. Our eyes cannot see ultraviolet. Some insects, by the way, can see ultraviolet. And we'll talk about that when we discuss biology and flowers later on. But what is shorter than ultraviolet? X-ray. X-ray is very short wavelength and extremely packed with energy. And that's why X-ray can go right through you, right through your body. When you go to the hospital, they take an X-ray. It goes right through your flesh. The only thing that stops them is your bone. Your bones are dense and strong enough that X-ray doesn't go through, and it will show. And so it carries a lot of energy, and that's why you should not be exposed to too much X-ray, because they carry so much energy. If you're exposed to too much X-ray, they can really cause damage to your cells inside your body, and you can actually die. If you are exposed to too much X-ray, you will die. So what is smaller wavelength than X-ray and higher energy than X-ray, but shorter wavelength, is gamma rays. Gamma rays are very powerful and very lethal. if you're exposed to gamma rays, you will die, for sure. Because even your bone will not stop them. They'll go right through your bones. So gamma rays are very energetic, very short wavelength, and very high energy. Okay? And we call the whole thing the electromagnetic spectrum. And we can only see a very, 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 very small part of it, the visible light, as you can see in the middle here. That's all we can see. The rest we cannot see. So we use equipment to see that. Like what? Well, look, for example, here you can use a remote control to control your air conditioner or your TV or your toy. And we use infrared. Well, infrared, do you see the beam that goes from your remote control to your TV? You don't see it because infrared light is not visible to us, but it's there. And the same with X-ray. You don't see it with your own eyes, but we can see the result of it going through your body because it's stopped by your bones, and that's why you can see an image of your bones inside your body with X-ray. And here's another example. Snakes actually use infrared sensing because infrared has a lot of heat in it. So snakes can sense that heat. They can sense the heat of infrared. And we also have cameras that can sense heat. So if this man is in a room and we are not in that room, we're outside of that room, between us there's a wall, we can actually use special cameras that can sense the heat through the wall and give us an image of that person. This is used also in weapons. Some weapons are equipped with infrared sensors so that the soldier who's using a rifle can see the person inside the room from their infrared radiation. So actually, as we go around our daily lives, every single one of us is radiating heat in the infrared range. And cameras can sense that. You can't see it, but it's there, and you can measure it with a camera. You can see it with a special infrared camera. So, here's something that's very, very amazing about light. You know what it is? It has a speed limit. Light goes at the speed of 300,000 kilometers per second. That's mind-boggling. Okay, let me help you visualize how fast that is. Our planet Earth is 40,000 kilometers in circumference. Okay? So light can go around planet Earth 7.5 times in 1 second. That's how fast it is. So light is very fast, and nothing can go faster than the speed of light. That's the maximum speed limit. It is 300,000 kilometers per second. So, we are 150 million kilometers away from the sun. What does that mean? That means that light from the sun to us will take 8 minutes and 20 seconds to reach us. So when you see the sun, when you see sunset and the sun is going down, actually at that moment when you're looking at the sun going down in the horizon, the sun is not there. The sun already went down 8 minutes ago. But the reason you see that it's going down now is because light took 8 minutes to reach you. Okay? So NASA sent a spacecraft to go to the dwarf planet Pluto, which is about 5 billion kilometers away from Earth. Okay? So that spacecraft, it's called the New Horizon, was going at the speed of 60,000 kilometers an hour. Can you imagine how fast that is? 60,000 kilometers an hour. And yet, it took 10 years to reach Pluto. 10 years. And light reaches Pluto from the sun. Light takes 5 hours, only 5 hours to reach from the sun to Pluto. So these are just some ideas to help you comprehend about the speed of light. So now, if we measure how far light goes in 1 second, we said 300,000 kilometers, multiply that by 60, you get how far light goes in 1 minute, and then 1 hour, and then 1 day, and then calculate for 1 year. And it turns out, if you do the multiplication, 300,000 times 60, times 24, times 365.25, you do the multiplication, you'll come up with approximately 10 trillion kilometers. So in 1 year, light can travel a distance of 10 trillion kilometers. That's 10,000 billion. That's 10 million kilometers in 1 year. So what do we call that? We have to give it a name. We call light year. A light year is a measurement of distance. Although we use the word year, which measures time, you have to be careful. Light year means distance, not time. And the light year is a distance covered by light in 1 year. And it's about 10 million kilometers, or 10 trillion kilometers. Okay? So, now we talk about energy. If you remember, we measure energy by multiplying the mass times the speed twice. Einstein, in 1905, figured out that matter and energy are interconvertible. That means you can change energy to matter, and you can change matter to energy. And if you change energy to matter, the amount of energy is unbelievably huge. Okay, let me show you how that works. So if you multiply mass by the speed of light twice, the mass of an object times the speed of light times the speed of light. The speed of light is measured in meters. So 300 million meters. Okay? 300 million meters times 300 million meters times the mass, okay, in kilograms, gives you the amount of energy in joules. So if you take only 1 kilogram, just 1 kilogram of mass, and convert all of that to energy, the amount of energy produced is equal to 1,000 atomic bombs. Stop for a minute and think of how unbelievable this is. Like 20 million tons of TNT. This is unbelievable. It's just incredible. So this is a huge amount of energy from 1 kilogram. So can you imagine if you weigh 50 or 60 kilograms and we change all of your mass into energy, then the amount of energy that your body will produce will be equal to something like 60,000 atomic bombs. So this is a very, very surprising and shocking, but this hopefully helps you understand the relationship between mass, light, energy. They're all interconnected and related. And the relationship is expressed with this famous formula, E equals mc squared. You see that on t-shirts, you see that everywhere, the most famous formula in the world. A lot of people know it, but they don't know what it means. So now hopefully this helps you understand what E equals mc squared means. Okay? There's something else that I'd like to explain to you that is very interesting, and that's the Doppler effect. You know, all of us experience that when you hear a police car or an ambulance or a fire truck. When they're coming from a distance, you know, you hear the pitch. But as they pass through and they come to you, the pitch becomes very, very loud. But as they go beyond you to the other direction, then the pitch becomes very, very low again. So it starts low, it becomes louder and louder and louder, and then it's really loud when it reaches you, and then after it goes away from you, then the pitch goes down again. Why is that? Well, here's why. When the ambulance is moving towards you, you have to remember that sound travels through air, right? You need air for sound. If there is no air, you don't hear anything. There's no sound. So when the ambulance is coming at high speed towards you, it's pushing and compressing, it's putting a lot of pressure on the air waves. So that's why the pitch, the frequency, you know, the wavelength is shorter, the frequency is very high, and you hear a higher pitch. It's very loud. So the woman on the left, on the other hand, because the ambulance is moving away from her, the air waves are spreading away from each other. They're going farther away from each other. And so the the sound that she hears becomes more faint and more faint. The pitch is much, much lower. And that is why she hears it more and more faint as the ambulance goes farther away. This whole thing was described by a scientist called Doppler, so we call it the Doppler Effect. It's very interesting. But is it only for sound? Does this happen only for sound? No, it also happens for light. So if you look at the sun at the top here, the sun is moving away from your eye. So because it's moving away, the light waves are more relaxed, they're longer wavelength. And what's longer wavelength in invisible light? We already know that. It's red color. So things will seem shifted towards a red color when light in the cosmos, in space, is moving away from you. If the light is moving towards you, then it's pressing the light to shorter wavelength, and we know that shorter wavelength is blue. And that's why we call that the blue shift. So this is how we know how objects in space are coming towards us or moving away from us. If they are moving away from us, there is a red shift because it's longer wavelength light, red light. And if it's coming towards us, then there is a blue shift. There is a shorter wavelength blue light. And that's very important for understanding many things in astronomy, and we'll explain that in the coming episodes. So these are the four basic forces of nature. There is the strong force. As you can see there are so many protons, but they repel each other. But the strong force is so strong, it is stronger than the repulsion force between the protons. The electromagnetic force of repulsion between the protons is very big. But the strong forces are stronger at very short distance. They have to be very close to each other, and they keep the protons and neutrons together inside the atom. Electromagnetism is when you have electron and proton opposite charge, negative and positive, they attract each other, or an electron negative charge, they repel each other. So all the electrons in the atoms in the center of the Earth, there's all that huge amount of pressure above them, and yet the electrons don't give up, they don't break. So this electromagnetic force is very strong, very, very strong. So the strongest is the strong force. The next strongest is the electromagnetic force. What's after that? The weak force. We will learn more about that in detail later, but the weak force, some atoms are not stable. They decay. We call that radioactive decay. That means certain particles and energy and light break away from the atom and leave it and go outside of that atom. We call that decay or radioactive decay. And there are weak forces inside the nucleus of the atom that make this happen. We'll study that in a bit more detail later on. The weakest force is gravity, which surprises, because here I'm sitting on planet Earth. I can't do anything because of gravity. I can't fly. I can't run very fast. I can't do much because gravity holds me down. And yet gravity is actually the weakest force we know. Of all the four basic forces of nature, gravity is the smallest one, or the weakest one. So why is that? Okay, look at this little boy, for example. The whole planet Earth is pulling that toy airplane down. And yet this little boy, about a year old, with his tiny muscles, is able to pick the airplane against the gravitational pull of the whole planet Earth and hold it up in the air. That's how weak gravity is. But on a large scale, on large distances, gravity is still felt. Gravity has an effect over long, long, long distances, almost infinite. So that's why we are 150 million kilometers away from the sun, and yet the gravity of the sun still holds planet Earth, and we're going in orbit around it because of gravitational force between us and the sun. We'll study gravity in a bit more detail in other episodes, but this is a good introduction. Also, here's another example of gravity. The Earth is heavy, and its gravitational effect on the moon is so strong that the moon is in orbit around planet Earth all the time. So that's the end of our journey for today. Hopefully you will join me for next journey. Our next episode is Once Upon a Time, my favorite story time, and we will talk about that in the next episode, and we start our story about the Big Bang and the creation of the universe. Thank you for joining me today, and I hope you come again, and bye for now.